Hi, welcome to my channel, JaberTime. Today I'm going to go over arc length and curvature. I have some graphs that tells you what's arc length and what's curvature, which is how fast the curve curves. In other words, kind of like in short. Let's get into it. I have arc length and curvature, and the first two graphs tells you something about the arc length. It's kind of related to calculus 1, as you could see, but we're speaking vectors. So by pointing to the point P, we have r of t. To point to another point after that, we're going to call it r of t plus some difference, h. So that's r of t, that's r of t plus h. Pointing to P and pointing to Q. Now, using vector subtraction, this vector right here is actually r of t plus h minus r of t. We know this. It's pointing to the r of t plus h. Now, speaking secant and slope and tangents from calculus 1, this would be the secant. This is the secant vector. And if you want to make h approaches 0, you are moving q closer and closer and closer to p, so it becomes a tangent vector. The tangent vector is dr dt, which is r prime of t, and that's the limit of r of t plus h minus r of t divided by h. That difference between here, t and t plus h. The unit tangent vector will be dividing the tangent vector by its magnitude. And that's what I have for this slide. Now, how do you find the length? Imagine if you have a curve which is in red going around this way, and you want to find its length. So you want to partition it maybe, and find this length, and find this length, and find this length, and keep going and add them up. That would be approximate. But if you want to make it happen accurate, using calculus and limits, you're going to take the limits and the Riemann sum and make it approach, the differences approach 0. So the length of the space curve is the limit of the lengths of those inscribed polygons or line segments. Here's the arc length. We know that the arc length is L equals from a to b integral of the magnitude of r prime of t dt. In plane curves, r of t is f of t I plus g of t j. R prime of t magnitude will be the magnitude of these, or this vector, with primes in it. And we know how to find the magnitude. We just take the square root, we square the first component, we square the second component, and we add them up. But this right here in a different language, so I could compare it to calculus 1, that's dx dt to the second, and that's dy dt to the second. In space curves, the only difference is I have f and g and h. 3 components. That's pretty much it. I want to save you some time instead of reading the whole thing, but that's the difference between plane curves and space curves. Now, the difference between those formulas and calculus 1 is we're not going with delta x as with respect to x. We're going with delta t. So the t is the parameter. That's why maybe it looks a little bit different. Find the length of the arc of the circular helix from the previous lecture video with the vector equation cosine t I plus sine t j plus t k. And we're going from 1, 0, 0 to 1, 0, 2 pi. Notice that I'm using green for this and this and this. So if this is t, I'm going from 0 to 2 pi. That's what I'm highlighting for you. And the helix that was graphed in the previous section was going around and round and round, but we want to stop at 2 pi. So we're going around back to the x-axis, but of course you have a value for the z component, which is going to take you up to pi value. Now they want to find the length. Okay, we're just going to use the formula and apply it step by step. We have r prime from r. The derivative of cosine is minus sine, the derivative of sine is cosine, and the derivative of t with respect to t is 1. We know how to find the magnitude. These two, they simplify to sine squared plus cosine squared, which is 1. And you have another one here, so you have square root of 2. Apply the length. That's from 0 to 2 pi. From t goes from 0 to 2 pi. That's my main variable, parameter. So I'm integrating from 0 to 2 pi of the magnitude of r prime, which is square root of 2, which is a constant. So the answer is, you multiply this by 2 pi, and we're done. 2 square root of 2 times pi. A single curve C can be represented by more than one vector function. I could skip this, but as I said before, it doesn't hurt. I'll go a little bit faster. At least you will be exposed to some ideas, because my lectures or my videos are more as like lectures with examples. They're not just examples. So let's go over this a little bit fast, just for your info. So we call this one under the topic parameterization of the curve C. So you could write the C to represent it with different vectors. Okay, in this case we're going to be calling it R1 of t and R2 of t, but they represent the same curve. Why is that? So this one is the twisted cubic curve t to the second, t to the third, where t goes from 1 to 2, could also be represented by e to the u, e to the 2u, e to the 3u, and u goes from 0 to ln 2. Now notice that t is being placed by e to the u. So that's the key part. Notice that we are going in R1. T is highlighted. And we're going to go t from 1 to 2. So let's plug in 1 in all of it. And let's plug in 2 in all of it. And I have it done for you. On the other hand, R2 of t is the following, and u goes from 0 to ln 2, so we're going to plug in 0 in all the components, and we're going to plug in ln 2 in all the components, just to verify. So e to the 0 is 1, e to the 0 is 1, e to the 0 is 1. Yes, it agrees with this one right here, the start point. Look at the last part, e to the ln 2, e to the 2u, but u is ln 2, e to the 3 ln 2, but we know that 2 goes up inside here, part of the rules of ln and logarithms. So I did that for you, and now ln and e cancels, and you end up with 2 to the second, and here the same concept, you end up with 2 to the third, exactly the same answer. Just to give you an idea that parametric curves could be written in different ways. Kind of like you use functions in calculus and use substitution and use U language. Looks different, and the limits of the integral looks different, but you are actually referring to the same area under the curve and the same problem. Suppose that C is a curve given by R of t equals f of t plus g of t and h of t, of course, I, j, k, where t goes from a to b, where R prime is continuous and C is traversed or traced exactly once at t as t increases from A to B. This is more like notes here in this slide. We define its arc length function S, this time they call it S, by S of t equals from A to t. See, the t is the variable and u is called in math the dummy variable. We have the magnitude of r prime phi du, And we know what is this. It's a square root. I don't want to read the whole thing. You could see it. We displayed similar ones a few slides ago. S of t is the length of the part of C between RA and R of t. What do I mean by this? I think visuals and graphs do help a lot in Calculus 3, and I take my time to graph it for you. So this, as an arc, length is called S of t. Okay? And it's between R of A and R of t as mentioned. If we differentiate both sides, this right here and this right here, using part 1 of the fundamental theorem of calculus, we know that the integration and the derivative are opposite operations. They're going to cancel. And I end up dSdt is the magnitude of R prime of t. Next, reparameterize the helix cosine t I plus sine tj plus tk. And one more time, I'm highlighting tk in green, or I'm using green to let you pay attention to that 0 right here. From 1, 0, 0 in the direction of increasing t, like, you know, it just keeps going. The initial point is 1, 0, 0. Corresponds to t equals 0 because, as you could see, the connection. From the last example, a few slides ago, we found for the same problem, ds dt is the magnitude of r prime, which is the square root of 2. So s is s of t, and the main variable is t, and u is the dummy variable. But this part was done earlier to be ds dt, which is square root of 2. Now, integrate this. That's going to be square root of 2 times u, and you're going to substitute t and substitute 0 and subtract. You end up with square root of 2t. They want me to reparameterize the helix. So now it's written in terms of the parameter t. Now we could write it in terms of the parameter s. So let's do that. From here, I could rearrange and write t by itself as s over square root of 2. We're pretty much done, by the way. All what you need to do is rewrite it instead of ts as a function of s, which is this right here. You could write s over square root of 2, s over square root of 2, s over square root of 2, and the same thing here, and we're done. Now, these components don't speak t, they speak s, so we are changing the language from t to s. It's going to be the same problem. Here's the second topic of this lecture, which is called curvature. What is curvature? They kind of write it small k tilted, but it's kind of hard by hand to make it perfect, but that's what I'm using for now. The curvature of C at a given point is a measure of how quickly the curve changes direction at that point. Imagine if you're driving in a car within circles. The bigger the circle, you don't feel that you are turning. The smaller the circle, you are turning faster, and especially if you're going with high speed. And that's kind of like to describe for you what's curvature. So the more that you curve, the higher the value of the curvature. So if you go with a bigger circle, like a circle with a diameter of 5 kilometers, you're not going to feel that you're curving. But if you go with a circle that is, what, 1/10 of a mile or a kilometer, so it's going to be a smaller circle, and you're going to feel that you are holding the steering to curve. So that's the concept of the curvature. This curve C, space curve, shows unit tangent vectors. One here, one here, one here, one here, one here, one here. You're going around this way. This is a high curvature. This is a smaller curvature. This is a very small curvature, and so on. You are curving here faster or higher in magnitude compared to curving right here. That's the curvature concept. Now, we define the curvature to be the magnitude, the value as a magnitude, of the rate of change of the unit tangent vector with respect to arc length. We use arc length so that the curvature will be independent of the parameterization, T or S. So K is, as it's mentioned right here, dt ds, and mentioned right here. T is the unit tangent vector, and S is the arc length. So if you write dt as dt dt and write ds as ds dt, now we have a different form. This would be called t prime of t, and this would be called r prime of t. So in short, this is what we have. The curvature has different formulas, and here's one of them. Okay, so you wanna make some notes out of this. Okay, this slide says it all. It's kind of hard like to keep repeating, so just make a note out of it and go back to it, maybe combine them in one page as formulas. Show that the curvature of a circle of radius a is 1 over a. A circle with center 0, 0 and radius a, we like to center it at 0, 0. It's easier to calculate and do the math. We have r of t to represent the circle as a vector function pointing to every point on the circle going around would be a cosine, not just cosine and sine, because that's going to be a unit circle, but they want the radius to be a, so we have to include a. A cosine I plus a sine tj. We know how to find r prime. The derivative of sine is cosine, sine of cosine, and the derivative of cosine is negative sine. We know how to find the magnitudes. Those are called ingredients to get to work, kind of like side work, if you want to call it. So the magnitude right here is a. Why is that? Well, if you pull minus a and square it, that's going to be positive a to the second, and this will give you a to the second. You pull it outside as a common factor right there. You will end up with inside sine square plus cosine square, which is 1. And we have the square root of a square is just a because a is the radius, which is positive. We're not going to use magnitude of a or absolute value. I think we're ready now. Let's take a look. T of t was mentioned as the unit tangent vector, which is r prime divided by its magnitude to make it a unit tangent vector. We have r prime, we have the magnitude. Divide this by this, a will cancel, as you could see. So what is t of t? It's just sine and cosine with the minus sign here and no a involved. Okay. T prime, just find the derivatives. So t prime magnitude is 1, and I think we're ready. This is side work for the formula. The formula is the curvature is the magnitude of the derivatives of the tangent vectors, unit tangent vectors, divided by the magnitude of r prime of t, which is, this is in green, which is 1, and this is the black, a came from here. Just plug them in. As you can see, it's a lot of work, but if you have the formula, you just need to get used to it and build it step by step. So what we have a circle with center 0, 0 and radius r equals a. And we came up with the curvature to be 1 over a. So some notes about this. This shows that small circles have large curvatures and large circles have small curvatures. This is the way I started talking about curvatures. You remember when I said like driving around a big circle and a small circle? Driving around a big circle, you're not going to feel that you are turning. And that's exactly what we have here. So a circle with radius a, when a is too big, like 5 kilometers, this is going to be 1 over 5 kilometers, which is a very small, tiny number. So the bigger the circle, the bigger the denominator, the smaller the curvature, which makes sense. Another comment. We can see directly from the definition of the curvature that the curvature of a straight line is always 0 because the length, the tangent vector, is constant. And if you go back, we are actually doing the tangent vector derivative will be 0 because the tangent vector t of t is constant, so t prime will be 0, which makes sense and it adds up. The curvature of the curve given by the vector function r is, here's another formula. This is a cross product. As you can see, we have enough components right here, so it takes more work, but it's straightforward. Find the curvature of the twisted cubic curve. R of t is t and t to the second and t to the third at a general point and also at the origin. As you could see, once you have all the components or the ingredients, you could go back to the curvature formula and finish it. Here's some work. R of t is, I wrote it down. I took r prime. You know how to do it. I took r double prime. Okay. Now I have r prime, I have r double prime. I need to do the cross product between them. Okay. R prime and R double prime, 1, 2t, 3t to the second is my second line. R double prime, which is 0 to 6t, which is my third line. And you know how to do the cross product. We cover this, and we call it I. And we multiply 2t times 6t minus 2 times 3t to the second, and we move on. That is going to end up with 6t to the second. 2 times 6, 12. 12 minus 2 times 3, which is 6, and that's 6. And, you know, the thing follows right here. We have a minus here. Don't forget to put the minus. We go plus, minus, plus. So now we have the top part, but without magnitude yet. So let's apply the magnitude. To find the magnitude, we square this, we square this, we square this, we add them up, and we take the square root. Simplify, 36, 36, and 4, they all divide by 2, or by 4, I mean. Take the 2 out. And now we have the numerator. Well, the denominator is almost ready. I mean, it's like this guy here. Magnitude will be like 1 square, 2t to the second, both, of course. And the 3t to the second also being squared. And we have the following. Because we have a square root inside, we have a 3. Square root means to the power 1/2. And to the power 3 means to the power 3 on top. So 3 and a half combined as power rules, will give you 3 over 2. Hopefully that's clear. I'm making it lecture notes, as you could see. Everything is right there, but it's kind of hard to slow down and read, like, you know, step by step, number by number, because that's gonna make the video too long, guys. So hopefully you understand that. If you feel like I'm going fast, you should know why. I don't want to make the video 45 minutes to 1 hour. Now, we have the curvature at a general point. We need it at 0. At the origin where t equals 0, we just plug in t equals 0, t equals 0, t equals 0, t equals 0, and we just do the algebra. K at 0 or at t equals 0 at the origin is 2. And that should do it. Here is another form or formula for the curvature. For the special case of a plane curve with an equation y equals f of x, notice this is different. Earlier we have f of t, g of t, h of t. Now I have y is a function of x. We choose x as the parameter and y follows, and write r of x. This is my I component and this is my j component. Y is a function of x. This is the formula that we use. F double prime magnitude over 1 plus f prime being squared, add them up and raise it to the power 3 over 2. Now you don't need to know everything about formulas, where they came from and how to justify things, but if it doesn't take too long and I could take the time to clean it up and write it down for you, why not? So let me show you too. Probably it's not going to take like maximum 2 minutes. So we know this formula, right? Y is f of x. X is my parameter. X, r of x is xi plus f of xj. R prime is 1i f prime of j. R double prime, that's going to be a 0 because it's just 1, a constant. That will be double prime j. Let's do the cross product. So as you could see, I know I'm going over deriving formulas or verifying, but actually we're using some skills of cross product. So there's a benefit for going over it. ijk, r prime from here, 1, f prime, and 0 for k. Don't forget that, 0 for k. This one here, only the j part. Only the j part, 0 for I, 0 for k. Cover this, times 0, go back times 0. You don't see the I part. Follow it, you end up with f double prime k. So that is the top part, magnitude, and the lower part from here, magnitude, and you wanna cube it. Sorry, went too fast. You have everything. As you can see, the cross product is f double prime. Take the magnitude, you will have magnitude of f double prime, because when you take the magnitude of this, you're going to square it, put it under the square root. Same concept. There is no k. R prime, here's R prime, I plus f prime x j from here. The magnitude will be 1 plus f prime to the second. Put them together and take the square root. It's right there. And with the square root is to the power half for the whole package. And we have a 3 here. That's going to show the 3 over 2. Find the curvature of the parabola y equals x to the second at the points 0, 0, 1, 1, and 2 and 4. So we have y equals x to the second, y prime equals 2x, and y double prime equals 2. We have the formula that we just mentioned earlier. We're going to use it now. And just plug in f double prime. The magnitude is going to end up 2. Same thing, 2 square under the square root is going to end up 2. 2x is going to go right here. That's y prime. Square it, that's going to be 4x to the second. Add 1 to it and put it underneath the exponent 3 over 2. Now we have the curvature. Let me explain the curvature. This is a great example to show you how to use this formula, and not only that, understand more about the curvature. As you can see right here, this function is a fraction. As the denominator increases, this decreases. In case of x equals 0, you end up with 2 over 1 plus 0, which is just 2. And that's this 2 here. This is the highest curvature. You curve here the max. Okay, let's stop talking right here and show you the numbers to save you some time. At 0, 0, you're going to plug in 0. Plug in 0, you get 2. At 1, 1, you're going to plug in 1 for x. Do the math, it's about 0.18. At 2, 4, you're going to plug in 2. Do the math, it's about 0.03. So the curvature here is 2. The curvature here is about 1, 1, which is 0.18. And at 2, when x equals 2, it's even less, because you're not curving much here. It's 0.03. As x approaches infinity or negative infinity, these are symmetric, as you could see, because if you plug in positive 5 or negative 5, it's going to end up the same thing. The second degree here will take care of the negative, and that's why we are symmetric on both sides. And here's a comment. As x approaches positive or negative infinity, the curvature approaches 0 because the curve becomes more flat, almost like going straight up. There is no curve. You don't feel that you're curving. This is the last part of this lecture. I could skip it, but it doesn't hurt to see those components within a clear graph. The normal and the binormal vectors. The graph says it. Let me go over it. T of t is a unit tangent vector. That's this one right here. And the magnitude of T of t is 1 for all t. T of t is defined to be r prime divided by its magnitude. That's why it's called unit tangent vector. N of t, this right here in red, is unit normal vector, is actually t prime of t divided by the magnitude of t prime. As you can see, the 90 degree right here tilted. So this is following the graph, and this is pointing in. So if you're going this way, that's going to point in. B of t comes in from the cross product between T of t and N of t. So you're going out, as you could see. B of t is the cross product between T of t and N of t. It's called the binormal vector. Is perpendicular to both t and n, and is also a unit vector. All these are 3 unit vectors. Why do we have them? There is advanced applications that they're used for. Because of the lecture, the video lecture, it's kind of hard to cover every single aspect in the book and call it a lecture video. That will be almost like a textbook. So that's why, to do my best to make my videos are a lighter version of your book, so you don't have to write the book or rewrite the book or underline words and lines in the book. So I'm doing it for you. As you could see, I'm taking my time to light, graph, underline, use different colors to highlight. So that's why I call my videos more like lecture videos, not just examples. Lecture videos with graphs and simplified examples. Once again, thank you for watching, and I'll see you in the next one. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.